Good evening, everyone. My name is Luke Westfall, and today I'll be talking about how to train your Pokemon neural networks. So I know there's a few people here who are a little bit older than me, a few people who are a little bit younger than me. So I don't know how many of you recognize that little guy right there, but this talk is going to be very kind of centered around that little dude. Funny enough, if you're into the lore of Pokemon at all, which I'm not totally into it, but Ash Ketchum actually isn't that same dude. I actually just learned that today. But anyway, I did dress up as Ash Ketchum. I didn't completely nail it. That jacket, I looked, okay? I looked, couldn't find it, but I got, the gloves are close enough, the hat, no backpack, but whatever. Anyway, what's the objective here? So we want to be able to train a model for agentic playthrough of Pokemon Red using reinforcement learning, starting from the beginning all the way to the end, defeating the Elite Four, the final bosses. And I'll kind of go over what each little bit of that means as we go. One thing I want to let you know, especially if you're not super familiar in the AI or ML space, machine learning space, what I mean by agentic playthrough here is I had to make this distinction for a friend that I rehearsed this talk with earlier today. He's super non-technical, and he's I'm 90% through the talk, and he's like, okay, I think I get it. But agents, what are those? And it's kind of important to have some basic understanding of what that means. So when I say agentic playthrough, that just means that we're creating a machine learning model that plays the game. And it's played inside the computer. So no human in the loop at all. We write the code that trains the models, but we don't play the game at all. Notably, we're not, the code we're writing isn't instructing the model or the agents how to play the game. We're not writing functions on how to beat this boss and how to catch Pokemon. These are machine learning models that you train and they learn how to play the game. So anyway, and also you might notice here this asterisk on beginning. I'm going to get back to that. Just keep that asterisk in mind for a little bit. But you might be kind of wondering, what's the point? Why would anyone spend time doing this? So applying machine learning to any kind of challenging task can lead to insights in other more important uses of AI. So JRPGs, which these Pokemon games kind of fall into this genre of JRPG, they have a lot of different gameplay mechanics that make this a really interesting task. So you have menuing, inventory management, battling, party building, and level, all these things. Exploration's a really big one, and we're going to talk about that. All these things are super important to be able to play an JRPG as a human, let alone as a computer. So that makes it a super challenging task as well. Yeah, in the back.
What's JRPG?
Oh yeah, thank you. JRPG just means Japanese RPG, I think. So RPGs are role-playing games, and then JRPGs are kind of a subgenre of that. Generally, they're turn-based, and there's probably other characteristics that make a JRPG a JRPG, other than the fact that they're Japanese. I wasn't going to take this tangent, but Claire Obscure, I don't know who's playing that. I think that kind of falls under the category of JRPG, but it's a French game, so I don't know. Someone can come up and correct me later, but anyway, yeah, thank you for the question. So here's just a simple animation of what it looks like for thousands of agents to be playing Pokemon Red at the same time. Now this isn't a real time, thousands of agents were actually running when this animation was made. It was kind of made in post, if you will. But I think it's just kind of cool, like it kind of helps illustrate the idea here. These are agents playing the game on their own from a machine learning model, and you can see them at various stages of the map. And another really cool thing kind of along these lines is that one of like the researchers who kicked kind of like this whole thing off, he made this tool, which we can try and visit here. Hopefully it works. Where it's kind of that same app, yeah, and it's almost like a Google Maps, whoops, of live, this is real time people training their agents, like playing the game, their agents are playing the game. You can see they're kind of moving at like hyperspeed because you want training to be short. But yeah, I think it's really cool to be able to see like what other people are doing. You can also see how yours are doing. I don't know, just like a fun tool that I wanted to show off. A funny side effect of that though is when I kind of jumped into this, like learning how to do this and doing it on my own, when I joined their Discord, one of these researchers was like, who is this Westfall guy? That's me. Their agents are moving like mine, which should be the case because I forked his repository, so I was kind of standing on his shoulders there, but it's really funny that he caught on to that. Like, obviously he's spending a lot of time doing this to be able to like notice the characteristics of these agents playing the game and be like, oh, his agents play like mine. Anyway, so let's talk a little bit more about Pokemon Red in general for anyone who's unfamiliar with it. So it was released in 1996 in Japan for the Nintendo Game Boy, and then later in North America in 1998. It's the second best selling Game Boy game of all time, just under Tetris, at like, yeah, 31 million copies, which is like insane. That's like, I think that's in like the top 100 video game sales of all time. So pretty impressive. And kind of just the basic, simplistic version of like the plot and gameplay is that you're a Pokemon trainer. Your kind of goal is to catch Pokemon and then use them in battles, either against other Pokemon, so you can catch those, or against other trainers who have their own Pokemon, and you're battling your Pokemon against each other. You level up your Pokemon by winning battles, and you earn badges at different gyms. These are kind of like somewhat major milestones throughout the game. They enable different learning new like moves and stuff that are necessary for progression, and like they're basically the bosses scattered throughout the game. And then you have the Elite Four, who I mentioned very briefly earlier. They're like the final bosses of the game. You beat the Elite Four, you win the game. So now to talk a little bit about reinforcement learning. I recognize that probably not everyone here has background in machine learning or specifically in reinforcement learning. So I'll try to keep this fairly basic, and the technical stuff doesn't last long. But this is just a very simple diagram where we have our agent at the bottom, we have our environment at the top, which in this example is just a maze, which I think is nice for explanation. So the agent can take some action in the maze. You know, you drop them in the middle of the maze or they start at the beginning. They can choose to go forward or back or left or right. Maybe they hit a fork and they can make a decision about where to go. So that's what kind of the action represents, is that decision. The environment is fed back into this like interpreter here, which is sort of like the model. When I say model, that's kind of part of it. And it outputs two things, a reward and a state. So the reward is some evaluation of what the agent just did in that environment and says, okay, like you moved a little bit closer to the exit, or you didn't turn right when you should have turned left. Like you get a point or 2 points, whatever. And you can also deduct points too. Like there are negative rewards you can assign. And you also give the state back to the agent. So with those two pieces of information, the agent is able to look at their new environment and say, okay, what is the next action I should take? And the agent is trying to maximize their rewards, essentially. So one more kind of diagram here, a little bit more going on. But yeah, this is like probably the most technical slide in here. And I'll pause before the next slide to give you an opportunity to ask questions. But this is kind of a high-level architecture of what these researchers are doing specifically with Pokemon. So the environment are kind of like those three blocks at the top. You have your game screen on the upper left, and that's three stacked screenshots from the game. And the reason there's three of them is because it's like the last three screenshots. And the purpose behind that is that it gives the model a little bit of a sort of like temporal reference to know like what happened a little bit before they took their last action, as opposed to just like what is the current thing. If you don't have any type of temporal information in the input to the model, it has a really hard time understanding, like it doesn't know the difference between what you just did, like just 2 frames before versus right now. So that's pretty important. They're also downscaled just because they can be, and it makes the training process faster. Another binary image, another image, which is a binary image of just visited coordinates in kind of like the current view of the screen. So wherever you are in the map, it's just like white squares for where you've been within there, and then black squares everywhere else. So it has some idea of where you've been and where you haven't been, which will be important later. And then your game state, which is just kind of like a simple vector of like, what are the cumulative levels of all the Pokemon in your party? What is the total hit points of your party at that current moment? What like badges have you earned? What milestones have you hit, etc. So each of those 3 pieces of environment information are fed into 3 different neural networks. 2 of them are nature convolutional neural networks, which are really good at taking images and like finding features in them, basically. And then you have a fully connected network on the right, and that's just, for lack of a better term, kind of just like your average or like most basic form of neural network. So the 3 of those networks output vectors from their inputs into an embedding, which is kind of just a combination of all those vectors. That puts it into a body, which is another fully connected network. And from the body, you get out 2 things. You get a policy head, which is basically, in a nutshell, just like the action. Like, what should the agent do based on these pieces of environment that we fed in? And then the value, which is, what do we expect the reward to be when we do this? So some estimation of the reward from that action. Any questions?
I'm going to touch on this in a bit.
Mm-hmm.
How do you decide what to reward?
Yeah.
I'm like curious about like the end goal is this one thing that you feel be really for.
Right.
But I imagine there's going to be some like intermediate steps. Like
For sure.
Meet all the intermediate velocities in this order because you can't.
Right, exactly. Yeah, an excellent question, which is like, how do you know what to reward, and like, what do you reward, and like, how do we build up these rewards in such a a kind of strategic way to beat the game? And yeah, I'll touch on that a little bit, but yeah, keep that in mind, and let me know if I miss anything there when I explain it. But yeah, that's coming right up. Any other questions?
So that's why all that logic, that's what you as the agent author are writing. Right?
Yeah.
Interpreting these neural networks, and each time if you get called, you bump out your action and your expected.
Yeah, exactly. So like the code that these people write, which like I might refer to them as we sometimes, because I dabble in this, but like to be completely clear, like I'm not a major contributor here. Like like there are researchers who are like way, way, way smarter than me who have done like infinitely times more work. But anyway, yeah, that's basically the code that they're writing is like makes up this architecture, or like this architecture is a big part of the code that they're writing. There's a lot of other stuff too, but this is kind of like the core of what is the agent, sort of like, and what are we really training here? Yeah, now might be a good time to actually mention that like both the action and the estimated reward, as well as the actual reward, is later fed back in to update these models. That's like a hugely important step. Otherwise, you know, these neural networks start out with like random internal values. You can think of them as like a bunch of little dials going on in there, and they just start out all at random positions. So at some point we update those neural networks. We just like tweak those dials a little bit based on some super fancy math to say like, okay, next time you see an image like this, you know, output something closer to this other thing. Yeah, I don't know. Yeah. Yeah.
And then the game screen inputs and the binary image, like that's just like the visible portion of the gameplay.
Yeah.
The entire map of the system.
So it's exactly what the player would see if they're playing the game. Like, I mean, aside from the fact that like they're stacked and then like downscaled. But before that, like post-processing, yeah, it's literally like the Game Boy screen. That's what we feed in the upper left. The binary image is like a slightly more post-processed version of that. It has some like very basic temporal information in there, but yeah, good question. Greg.
Just like a comment on that. So like with the power of emulators, like you could give the AI a lot of detailed information about the internals of the game.
Yes.
But generally speaking, for people who work on stuff like this, that would be cheating.
Yes, exactly. Yeah, thank you. Yeah, you're totally right. So like we want to be really careful about the type and amount of information we feed into these networks. Not only because the more information you're feeding in, the longer the training process, the bigger your networks are, the more memory usage, et cetera. It all kind of like snowballs. But yeah, also because like, yeah, you could tell it like almost exactly what to do next, or you could give it information in the Game Boy's memory that the human player would never know. Like, but like that's not as fun. That kind of defeats the purpose. Like, just write a program that plays the game. Then, like, why are you even using neural networks at that point? So yeah, great point. Thank you. Any other questions? Yep.
How complex can policy be? Can it be like navigating through a menu, or is it literally just kind of?
So it's a good question. I will say in this case, what these researchers are doing is the policy is, it always results in just a single button press. It's up, down, left, right, A, B, or start. There's also a select button, but they don't use it. It's useless for this game. So yeah, it's just one button press is the action in this case. But in general, I would imagine, yeah, you can make policies about as complex as you want, you know, within, again, like the more information you're outputting, I would imagine you also run into needing bigger networks to crunch more hardware, et cetera. Good question, though. Anyone else? All right. So how do we evaluate agent performance? So we kind of went over this a little bit. We write reward functions that add or deduct points based on events and basic statistics. For example, we add points when a Pokemon gains a level, and that kind of diminishes with level. So the further you go, the lower the reward. So that really incentivizes like early leveling up. Give 2 points for certain types of events, winning trainer battles, etc., certain quest progression events. A small reward for newly visited overworld coordinates. So as you move through the map and you visit a new coordinate, you get a little bit of a reward. Points for healing, making sure that if your party's low on health, they're regularly visiting Poke Centers and getting health so they can win more battles. But then what? So again, I kind of talked about this a little bit before, but we update the model, all those neural networks, based on agent performance to encourage improvement. So the way that works is we kind of break it down into episodes, an episode being a certain number of steps, where a step is an action that was taken. So let's say an episode is 10,000 steps long. At the end of those 10,000 steps, we stop all the agents. You have a bunch of agents running in parallel to speed up training. You stop them all at that point. You analyze what they did and kind of like which agents performed well, what they did, feed that back into those neural networks, update those knobs so that the next time it's playing, it's using those new values and doing better. So in theory, you're encouraging improvement there. We also use what you were looking at before is a proximal policy optimization architecture. And kind of to make it super simple, that just means we're making really, really small changes to those knobs. Because if you change them too much, you might push it way too far, like past the point of no return. You can kind of think about it as you're balancing a broomstick on its handle. You want to do like small adjustments, big adjustments, you end up falling over. It's the same kind of thing. So reward shaping. So I'm going to talk about an example of this in a little bit, but sometimes the reward event is just a little bit beyond like the horizon. So we were just talking about these episodes. Sometimes the rewards you want, you don't ever expect it to be within that 10,000 steps. So that's like a pretty difficult problem because sometimes these are really like discrete events. What we can do with reward shaping is like try to figure out how to break that down into like intermediate steps and reward those to encourage moving towards that bigger reward, even if it takes more than 10,000 steps to get there. So some of these sort of big challenges that these researchers have run into. Exploration, we talked about this a little bit, but specifically the very first quest of the game, basically, one of the first things you do is choose your Pokemon, and Professor Oak, who gives you this like free Pokemon, says, hey, go to Viridian City, there's a package there for me, bring it back. It's like the very first thing you do, basically. Bring it back to Pallet Town where Professor Oak is. The problem with that, we talked about the exploration reward a little bit earlier where newly visited coordinates are encouraged, but kind of like conversely, visiting old coordinates is discouraged. So in order to complete like the first quest in the game, you have to backtrack, which we don't reward that, we don't encourage that. In fact, like we kind of discourage that. We want the agents to progress through the map rather than like going in circles or whatever. So how do we fix that? So right now, we kind of cheat a little bit because it's like a surprisingly hard problem. Some of you are probably trying to think of like reward functions that get around that. And maybe there's probably something out there, but it's a really hard one that they haven't figured out yet. And in order to like make progress with like this research project, we cheat with a save state. So like the save state starts right after you complete that quest, because from there, like pretty much the rest of the game doesn't require backtracking. So that's one big challenge. Another one is the Safari Zone, which is a special area of the game, kind of like a quest on its own, where you are given 500 steps to kind of complete this quest, like 500 steps being like footsteps that the character takes. And if you exceed that, then you're like reset to the beginning. So this is like hard for agents to deal with because 500 like footsteps can translate to like many thousands of, or even tens of thousands of steps from the model's perspective, like actions being taken, button presses. So that's one example where the reward of finishing the Safari zone is beyond that 10,000 step horizon. It could be at least that long. So yeah, the regular exploration rewards don't apply here. Like you'll never finish it in 500 steps. So the solution to that is, again, reward shaping. We talked about that. So this is like a very active problem. Like I don't have a solution, like a solution longer than 2 words here because they're still actively looking at this. They're using reward shaping, but they haven't nailed down the best way to do it, to like basically guarantee that most agents are making it through the Safari zone. Yes?
So like when the basically the dynamics of the game change, like you haven't evolved or worked on something like, okay, now we're in a different phase of the game, there's different objectives.
Yeah.
Change.
Sort of, yeah. I mean, it's one of those things you want to be really careful about, to Greg's earlier point, where you don't want the reward functions to be so specific to phases of the game that like you're basically cheating, you're basically writing code that plays the game. But yeah, for stuff like this where the mechanics are so different, like any other exploration-based reward function is just not gonna work for like the rest of the 98% of the game and this part right here. It's just so different. So like I think it's just one of those compromises where it's like, okay, like we need a different type of exploration function here. And that's basically what kind of another part of what reward shaping means, is figuring out where to have reward functions that make sense. Yeah.
Is your reward function supposed to be set up like ahead of time?
Yeah, great question. Yeah, so that's another part of the code that they write before the training process. So the question is the reward function something that's like known ahead of time? I will say it's not known by the agent. The agent, the only information the agent has is basically the action that the neural network is given. So the agent doesn't even know like when to expect a reward. It's just doing stuff, and over time, it's kind of guided to reach those rewards. But yes, the reward functions are written ahead of time by the programmers. Yeah.
It sounds like these need to be dynamic, like these have to input into the reward function.
Yeah, you can kind of think of it this way. So the Safari Zone exploration reward function, you can think of whether or not you're in the Safari Zone as that input. It's like if you're not in the Safari Zone, which is most of the game, then use this regular exploration function. Otherwise, use this more specific, like purposeful one that works. So another big challenge is training time. So anyone who's ever dealt with training machine learning models or anything like AI related knows that it takes usually a little bit of time. You need pretty good hardware, but usually you're mostly interested in like having a good GPU, something with a good clock speed, and especially like a high VRAM or some high amount of shared RAM. But in this case, we're working with emulation, which is CPU and like regular RAM bound. So you can have the best GPU in the world, and it's really not going to help you that much here. It will help you a little bit for like the convolutional neural networks, or updating the neural networks and running through the neural networks. Those will use the GPU. But most of the time spent training these models is the agents playing the game, which is an emulation. So a complete training run takes like multiple days. Like I have one that took 40 hours, and it didn't beat the game. So yeah, another kind of fair challenge there. So one thing some people might be wondering is like, where do LLMs fit in here? We've talked solely about these kind of more traditional machine learning methods, and we haven't really talked about LLMs. But they are kind of in this space a little bit too. Not directly with what the researchers I've been talking about are doing. They're not leveraging LLMs, but Anthropic has done some work. So this link here links to this like agent that, or like agentic workflow that Anthropic built to play Pokemon Red using Claude, which I think is really cool. To my knowledge, I don't think they've beat the game, although Michael was telling me earlier that they made some announcements with Claude 4, which like just came out relating to this, so I actually haven't like read about it yet. So it'll be interesting to know like how that's helped. But yeah, this is just a screenshot of that Twitch stream. You can see on the right, like it's the screenshot of the game, and then on the left is literally what the LLM is thinking. Like, what do I need to do next? It's like, I need to continue my search for the actual Route 5 entrance. Let me continue exploring, blah, blah, blah. Let me try moving east to do this. I'll move back and do that. But at the very bottom, you definitely can't see it, but it says buttons A, which wouldn't do any of those things. So like, it's kind of funny. Like, I went to Twitch just to see, like, just to check it out and grab a screenshot, and like, it seems like it's kind of stuck there a little bit, but still super cool. Like, in many ways, very different from what we're doing, but also kind of helps illustrate that like, there is interest about these games in the AI space, even from these like huge companies. So pretty interesting. And then, speaking of recent news, at the Google I/O keynote, which happened on Tuesday this week, Sundar Pichai talked about Gemini and how it beat Pokemon Blue, which is really cool. But like, as researchers who are more interested in the RL thing, it's kind of like, man, like the LLMs won, like damn. But at the same time, it's Pokemon Blue. It doesn't count. We're talking about Pokemon Red, totally different game. No, I'm just kidding. They're basically the same game. So no, but I think it's so cool. Like where LLMs are fitting in here. It just kind of shows like how interesting these games are as a way of like benchmarking or even simpler than that, just like a fun way to like relate to like regular people who played these games growing up, like me. To show off like the advancements in their technology. I think it's just so cool. So really excited to see like what other games they start playing, more complicated games. What's that? Zelda, yeah, that'd be a great one. There are other researchers in that Discord who are experimenting with other games. I know like Metroid is another one, and Zelda would be really cool. But yeah, if you want to try this on your own, you totally can. These links are impossible to read, but there's a QR code later if you want these slides, and I'll post them in Slack and everything. But yeah, my recommendations is to use a Linux environment. I haven't tried macOS, to be fair. That might work totally fine. WSL, I think some people have done it. I wasn't able to get it to work on my own, so I did have to spin up Ubuntu for that. But yeah, from there, choose a repo to start from. I would recommend that at least, unless you're like a whiz at ML and you want to just do it from scratch, by all means. I can't, so I tried out both of these repos. And there's other ones in the Discord, which I also have a link to there. The Discord is huge, great community. Any issues you run into getting set up or just looking at like kind of the ideas that they're talking about to improve their models, like it's just really cool. Super nice people. Or maybe you want to go like the LLM route, which is really cool too. And it's getting easier and easier every day to do that kind of thing, to build your own agents and workflows and everything. Yeah, if you do that, definitely let me know. But yeah, just a couple very quick shout outs to some of the tools that are super important here. We talked about emulation. PyBoy is how we do that. It's a Python-based Game Boy emulator. Super rich API for being able to interact with it, take screenshots, button presses, do all the things that we need to do. It's super fast. And then weights and biases, if you haven't heard about this, it's just a web application where you can kind of like stream telemetry up from your training process so that you can see what's going on without having to like watch video playback or something of your agents. Yeah, super important way to see what changes are working and what aren't. And then, yeah, a whole bunch of more resources here. I won't go over all of them. All I'll say is the very first one is a YouTube video. It's like, I think like 30 or 40 minutes long, and that's what inspired me to get into this. And like, if you're interested in this at all, definitely watch that video. It does a way, way, way better job of talking about this topic than I did. And it also kind of like relates it to like, kind of like the human conditions and stuff in like a really interesting way. So yeah, definitely check that out if you're interested in learning more. And then there's other stuff on here too. But yeah, if you want to see these slides, get those links or whatever, you can scan this QR code. Or again, if you're in Slack, I'll post it on Slack after this. But yeah, otherwise, any other questions? Ooh, right here. Yeah, you right here.
What's the best name for a Pokemon when Greetings is picked?
Oh, I don't. That is such a good question. I think usually they just name it like A, like yeah, because like there's no rewards for like good names, but that would be like a really fun like. Yeah. It would be fun to come up with like a meme, like memed like version of the model that is trained on reward functions like that, like funny names and like.
Weird stuff that people do. Like,
Yeah.
things that just like.
Yeah.
Keeping your starter could be good for that as well.
Yeah, right. Yeah, keeping your starter could be good for that too. Yeah, for sure. Tim.
So when you pause it or when it finishes, can you dump the game state and say what Pokemon are in this agent's party, what level are they?
Oh yeah. Yep.
What do they know and all that?
Yeah, that PyBoy emulator, you can peek at like any RAM location. So like basically anything you can think of, you can do it. I mean, it might be really complicated to do it. Like reading memory from a Game Boy, like isn't always straightforward depending on what kind of information you're trying to get. But yeah, you could totally do that. Yeah.
Or have you decoded it down to like this is my most successful agent? What does it have?
Oh, yeah. I mean, that's the most successful agent. Are you talking about like determining the most
I want
successful?
to know what Pokemon he has.
Oh, okay, yeah. Yeah, you could totally, dump the game state and like, write some kind of function to translate those memory values into, what did their party look like, yeah.
Because the real end result is what is the most powerful and best.
Yeah, I mean, you can also just have a record video of the game too, and output that to an MP4. Yeah, you can totally do that. Just a couple more questions right here.
Yeah, I was asking about the reward function earlier.
Yeah.
And in my head, the end all be all, right, is that it sees screenshots, it plays the music or whatever,
Mhm.
and then it feeds the report. No human input.
Yeah.
to the rewards. Is that just out of the scope of what we can do with our current computation? Like the number, that's like the number of chess moves in the universe or whatever?
I think it's more, if I'm understanding the question correctly, which what I'm hearing is like, why isn't the human in the loop kind of? Like, is it because it's,
Is it just too computationally intensive
okay.
to not have any reward function at all? Like other than
Oh.
that can be game mechanics.
No reward function at all? Like,
In my head, when I play Pokemon, I have my thumbs and my eyes and my ears.
yes. So, okay, I think I know what you're getting at here. So my response to that would be, there are reward functions firing in your brain as you play the game. When you beat a gym leader, and maybe you've been stuck on it for a while, you're like, hell yeah, dude. Like the dopamine rush in there, like they're literally called reward centers, and like they are like very very analogous to like what we're talking about with these reward functions here. So does that answer the question? Okay, yeah, thank you. Yeah, it's a great question. All right, one more right here.
Yeah, just curious, that repo, like what libraries was that based on?
Mhm.
Have you explored other reinforcement learning libraries, and what would you recommend if you all not some that are like really easy to use compared to things a couple years ago? So I'm just curious.
Yeah, so I think most of these are torch-based, I want to say. PyTorch, if you've ever used that. There's also this library that one of them uses called pufferlib, which, to be honest, I don't know that much about, but I know it's like a big, like kind of emerging like RL-specific framework. So like, and Pokemon's one of the big games that's being done using that. But there's also like a lot of others that are really interesting. None are coming to mind, but like mostly like Atari games and things like that. So I don't recall like specifics about a lot of the libraries, and part of that is because they've made it so easy to kind of like, I don't want to say steal their work, but like kind of like start from where they are, because it's a lot for someone like me to just kind of do it from scratch. So it's a really good question, but unfortunately, like I haven't dug deep enough to know the finer details about what they're using. But yeah, any other questions? Yeah, come find me, hit me up on Slack or whatever, but thank you guys so much. It's awesome.